Hello everybody, this is Mr. McAllen, and we're going to be talking about today some general concepts about functions that we should always think about when, no matter what function we're analyzing. And what we're going to do is we're going to do three concepts that deal with increasing and decreasing of functions and naming those intervals on which they increase or decrease, talk about boundedness of a function, and talk about if a function has a local and absolute or local or absolute extrema. And I'll explain what that is when we get to it. But basically those are, when you're looking at a function, describing like the highs and lows of the function and where they occur. So in the first example here, I've plotted on Desmos, and you can plot this too if you want to examine it. I've plotted a polynomial that is x to the fourth minus 7x squared plus 5, and I've called out some points on the function, but the purpose of this is because this function, based on the graph, we have to assume it keeps going on in these directions. And we want to just talk about the idea of increasing as opposed to decreasing for the function. So increasing versus decreasing. So the concept graphically should be really easy to understand, but you'll be surprised how many people reverse the two, because when they look at a graph and they see the graph is going up, they think that it's always increasing. But this is, you have to imagine that you are looking at the graph from left to right, or you're examining the graph as x increases, as x is increasing. So as x is increasing, as you're heading this way on the x-axis, if the function is going up in value, the function value is the y value, then the function is increasing. So, for example, on this graph, we see that the function, as we progress this way on the x-axis, the function is heading down, and that down is decreasing behavior. So on the interval and I'll just like write out the interval. So I'm just going to shade in. I'll say this is a decreasing interval. And then up until this point here, this is an increasing interval. And then up until this point again, we're decreasing. And then the rest of the way, the function is increasing. So this would be correct in terms of describing where the function is increasing and decreasing. But the other thing is we need to write this in interval notation. So I'm just going to move down a little bit, and so if I wanted to say, if I wanted to say a statement for this, I would say f of x is decreasing on the interval from negative infinity, comma, up to 1.732, and on the interval, so the next decreasing interval would be from 0 to 1.732, and that's all. Those are the only intervals where we're decreasing. And then I would write, I'm just going to change the ink color. I would say f of x is increasing on the interval from 1.732. It's increasing on this interval here, which I have labeled on the number line. So that's the first interval I'm going to write, is from 1.732, comma 0. Oh, not 0. That was negative 1.732. See that? My marking kind of masks that, so I've got to make that correction there. And then that means that has to be negative 1.732 to 0. I apologize. And on the interval from 1.732 here to infinity. So hopefully this helps explain like how we describe increasing and decreasing intervals for a function. Remember, hopefully next year you'll be taking calculus. We'll have a lot more advanced methods to describe increasing and decreasing intervals. Especially, we're relying upon the graph to tell us this. So if your graph doesn't have all the information, or you can't see all the information, you may not be describing the right intervals. So we'll always want to make sure that your graph shows enough information to be sure about your conclusion. Now we jump ahead to the idea of boundedness, the idea of a function being bounded above or below So what you basically do is you look at the graph and you see, like, is there a boundary which the function will not cross? So on this on this graph right here, we clearly have a lower boundary, and that lower boundary is at -4. So the function never goes below the value of -4. So you would say for this function that the function, if you want to make a boundedness statement, you would say the function is bounded from below by the line, or by the value y equals -4. The function is not bounded from above, even though you might see that, it looks like it's bounded here in a local sense. The function, it has values which are higher than 5. So this function is only bounded from below. Now we turn our attention to another example, and what I'd like you to do is, if you take the time to plot this on Desmos and then look at a picture of it, you would see that the graph would appear to be, from the left, it appears to be decreasing, and then it's increasing, and then decreasing again. So it would appear from the graph that the function is bounded from both above and below. It never gets above or below these values. So your explanation for boundedness based on this graph, remember, it's always based on the graph that you're looking at. So you would say f of x is bounded. You just say is bounded. Now when you say it's just bounded, then we interpret that as saying, like, it's bounded from above and below. So you say it's bounded by the lines, or the values, y equals 0.5 and y equals -0.5. You don't have to say bounded from above and below. If you just say bounded, we'll assume, or everybody will assume, that your stating is bounded from above and below. If it's bounded from above or below, you've got to state which it is. So I'm going to move on to the next example. Okay, so we're on to the next example, and this is where we talk about local extrema and absolute extrema. So I'm going to first talk about what are called local or relative extrema. Now, extrema is referring to a maximum or a minimum value. Okay, so local means in a certain area of the graph, like, as for example, this local area of the graph. If you were to just zoom in on this area of the graph, and well, I'll zoom in on it just so you could only see that part. I hope I have enough zoom capability. So if you were to just zoom in on one more, let me see if I can zoom in one more time. All right. So if you were to just look at this part right here, and you didn't see these lines, and you would say that this is a max, but it's really just in the local area of this window here that is a maximum. So this would be called a relative or local max. But you could see when we zoom out, it can't be an absolute maximum, because let me zoom in a little bit more. That's going to be, we went really too far out. Here. So you could see here, if you look to this side and this side, that the function clearly gets larger than the relative max, but we can still describe a relative max on a local sense. So anywhere you see the function. So what's the rule for this? How do we come up with this? Well, okay, so the relative max rule is the following. If f of x changes from increasing to decreasing, then you are guaranteed, or then you definitely have a local max or a relative max. If f of x changes from decreasing to increasing, then you have a relative, oh, I should say local. Local, relative, the same thing. Local min. So let's look at this. So if we look at the function, just going to zoom in. If you look at the function in this interval, the function was decreasing, and in this interval, it's increasing, and that means that at this point right here, we have a relative min value. Okay? So when you go to the next interval, we change from increasing, so here we have increasing, changing to decreasing. See how the function is like the top of a roller coaster, and then you go down. Well, when you go from increasing to decreasing, you have a relative max. And then when you are on the roller coaster heading back down again, you're going from decreasing to increasing. That point where you change is another relative min. So it seems pretty simple, but when we ask you for an explanation on what the relative max and relative min is and how you know you have one, we need to see you explain it with these explanations. So the way you would say your answer, if the question said, okay, so I've written out a question where this is a typical question they ask in the book. Use the grapher, or a grapher, to find all local maximum and minimum values of x and where they occur. Justify your answer. Okay, so we have the graph plotted. That's what will be given to you. So the first thing would be, I would say, well, I have a relative min. So a relative min, or local min, exists at x equals negative 1.732 and has a value of the y value, which would be negative 4, and the justification would be because f of x changes from decreasing to increasing at this point. I would then say the second thing is I have a relative max. So I'm just basically going across the graph. I would say I have a relative max exists at x equals 0 and has a value. Now remember, the value is again the y value of 5 because f of x changes from increasing to decreasing at this point. The last one, hopefully you've guessed it, I have a relative min at x equals 1.732 because f of x, oh, and has a value, don't forget to explain the value, and has a value of negative 4 because f of x changes from decreasing to increasing. So, anyway, hopefully this helps make the, of course it's easy to notice a relative max and a relative min, and but we have to justify our answer and we have to write it out properly. This is an important skill for mathematics in the future as well as for this year. And the idea of absolute max and absolute min is simply tackled once we understand how to name the relative max and relative mins. So hopefully this video helps get you ready for our day in class coming up the next time we meet. And I look forward to hearing your comments.